Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In today's lecture, we will continue our discussion on the solutions of hydrogen atom problem. If you remember, we saw that the quantum mechanical solution of hydrogen atom that we obtained closely agrees with the Bohr's atomic model. In particular, the energy level expression as well as the maximum probability, the radius at which the electron is going to be found with maximum probability, that turned out to be the Bohr radius for 1s orbital. While the Bohr's atomic model had good number of agreements with the quantum mechanical formulation of hydrogen atom that we had in last few lectures, but then there are some cases where the Bohr's atomic model could not explain some experimental results. For example, the emission spectrum of hydrogen atom in the presence of external field such as magnetic field or electric field could not be explained by Bohr's atomic model. Today in this lecture we will discuss this particular effect. In particular, we are going to discuss the Zeeman effect or the emission spectra of hydrogen atom when it is subjected to a magnetic field, an external magnetic field. Now, the point is, why would the atom, that is hydrogen atom, interact with this magnetic field or would have any term of any relation with magnetic field? Why would the magnetic field be able to perturb our system, that is the hydrogen atom? To do that, let us see what we know from classical mechanics. We know that if there is a charged particle which goes around a loop, a charged particle with charge q and mass m, if it goes around a loop, it actually creates a magnetic dipole moment, and this magnetic dipole moment is, the vector is given by this relation. Where q is the charge, r and v are the displacement and the velocity vector, and this is a cross product of the two vectors. Now, we can rewrite this by introducing a mass term both in denominator and numerator, and in particular we do this, we rewrite this expression in this particular way, where m is the mass of this particle which goes around this loop. Now, if you look this expression closely, you will see that this is displacement vector and this is linear momentum vector. So, the vector product of these two vectors would give me the angular momentum vector, which is now multiplied by the charge of the particle and the mass of the particle. So, whenever a charged particle shows a circular motion, it develops a dipole moment, magnetic dipole moment, which is given by this expression q divided by 2m multiplied by the angular momentum vector. Now, this is what we know from classical mechanics. Now, if I have to formulate this in quantum mechanical sense, so that means the operator corresponding to this dipole moment would turn out be, so if you remember in quantum mechanics, the postulate number 2 suggested that for every classical observable we can write the quantum mechanical operator. So, the quantum mechanical operator that I can write for this system is simply this L operator, because L, the orbital angular momentum operator, corresponds to this L vector, the orbital angular momentum vector. Remember, this is a vector operator, and we have already discussed quite a few things about this angular momentum operator. Now, we have this magnetic dipole moment that is already present in our atom. Why? Because in our atom the electron goes around the nucleus in a circular path. Now, since the electron is already going around and it has developed a dipole moment, now if I subject my atom to an external magnetic field with field strength of B, then this magnetic dipole moment that is being generated by the orbiting electron will interact with this external magnetic field. By the very fact that the electron is a charged particle which is orbiting around the nucleus, develops a magnetic dipole moment, and this dipole moment interacts with the external magnetic field. As long as you do not have this external magnetic field, the dipole moment is there in the atom, but it does not show its effect or it does not manifest in any of its properties. But when we apply the external magnetic field, now the manifestation of this dipole moment operator that is already there in the atom comes out. So, this is what we are going to discuss. Now, in the absence of this external magnetic field, the Hamiltonian of our system, which is now hydrogen atom, is given by the kinetic energy of the electron plus the potential energy of the between the electron and the nucleus, which is given by a Coulombic interaction. Now, this is the original Hamiltonian that we had, and you see even when this electron was going around this orbit the nucleus, it had this dipole moment, but it was not being visible in this Hamiltonian yet. But when I apply this magnetic field, external magnetic field B, this magnetic dipole interacts with the magnetic field and it creates a new kind of interaction, which is a kind of a potential energy interaction. So, this V magnetic, or we write V magnetic, which is the potential energy that is coming out because of the presence of the magnetic field, and which is now interacting with the electron's dipole moment, because electron is orbiting the nucleus. This potential energy is given by minus mu dot B. So, mu and B. So, we are writing here the scalar product between the two vectors. If we apply this magnetic field only along z direction, so therefore, only I have only Bz term active, Bx and By are 0, and since I have this dot product here, so this would simply mean that I have mu z Bz. This is now the potential energy that I am getting from classical mechanics description of the system. Now, corresponding to this potential energy, I can write down the potential energy operator Vm. What would that be? I see that this is the classical mechanics relation. So, the potential energy would be simply mu z operator multiplied by Bz, where here Bz is simply the external magnetic field, the strength of the magnetic field that I can, when I am doing the experiment, I can tune. So, now this operator has become, so since Bz is a constant that depends on the experiment, and mu z is already, you can see here, q divided by 2m, and instead of writing L operator, I write Lz operator. So, this is the quantum mechanical description of the mu operator. Now, the potential energy arising because of the interaction of the orbiting electron with the external magnetic field is given by this term. Now, when you do not have this magnetic field, this Hamiltonian is sufficient, because this talks about the kinetic energy of the electron and the potential energy between the potential energy corresponding to the attraction between the electron and the nucleus. But when you have magnetic field, then you must add another term. So, this term is your Vm, or the magnetic field interaction that we have here. So, now we have a new Hamiltonian. So, this was the original Hamiltonian, let us call this H0, and this is the new term that we are adding. And why is it being added? Because I have applied the external magnetic field. Now, in this new Hamiltonian, what would be the energy? So, in other words, what would be the expectation value of this corresponding to this Hamiltonian operator? So, to obtain that, we would simply now write the expectation value corresponding to this operator, where we know that the wave function, total wave function of this the hydrogen atom is given by the psi n L m. We already know their functional forms. So, this is what would be the expectation value or the energy expectation value corresponding to the Hamiltonian operator or the average value of the energy. So, now we see that this Hamiltonian has two terms. So, the first term plus the second term, which is now look at the first term. What is this? I know this I n L m is an eigenfunction of S0, and in fact, the value of this. So, since this is an eigenfunction of the Hamiltonian, so at the end I would actually get the energy, and this energy I am writing it as E n L m. So, this is the hydrogen atom's energy levels that we already know. But if just to remind you, hydrogen atom's energy did not depend on L and M, it had only n dependence, because we saw that for nth level there are n square number of different eigenfunctions. So, this has n square this is n square fold degenerate, and it only the energy depends only on n, or the principal quantum number. So, I am just writing, instead of writing n L m, I am just writing n E n. Now, let us look at this new term. So, I have this V m which is given by this expression here. So, to take care of that, I see I would have to put this term over here. So, let us do this. I see that B z is a constant, because this is the applied magnetic field. Q is the charge of the particle, and my particle at the moment is electron which is going around. So, therefore, Q is in the case of electron, Q is minus E, and m, the mass of the particle, is mass of the electron. When I put Q as minus E, so this term becomes plus. So, therefore, I have B z E, which is the mass charge of the electron, divided by 2 mass times mass of the electron, and this is now the operator. So, I would actually do this, I will keep only the operator part inside the integral, outside I brought the constants outside. Now, let us look at this relation. The question that I ask now is that, is this psi n L m, which is the eigenfunction of the Hamiltonian of hydrogen atom, is it an eigenfunction of Lz operator? The answer is yes, because psi n L m has a radial part and an angular part. The radial part does not get influenced by the Lz operator, but the angular part, which is the spherical, spherical harmonics, this is actually the also an eigenfunction of Lz operator. So, when Lz operator acts on psi n L m, one of these eigenfunctions of hydrogen atom, so the result is simply m h bar psi n L m, because you see this psi n L m will have a radial part and an angular part, and this angular part, the spherical harmonics, is an eigenfunction of this Lz operator. So, therefore, the result of this is m h bar, where m is the quantum number, and then I still have since I have already applied made the application of LZ operator in this function, I have mh bar and the function itself, and then when you see this overlap integral, since psi NLM is normalized. So, this integral becomes 1 and therefore, I am left with the terms is that E n plus E divided by 2 m E h bar m beta z. Now, look at this term. So, I have E m. So, this m is the magnetic quantum number of the corresponding to the state. This m e is the mass of electron, E is the charge of electron, h bar is Planck's constant divided by 2 pi and 2 is a constant. So, I see all these constants, if I use them, I give a new name to this, and this has a famous name. This is called Bohr Magneton, whose value is given as 9.274 into 10 to the power minus 24 joule per Tesla. So, this is Bohr Magneton. So, we have this new constant beta, which is known as the Bohr Magneton, given by this value. Apart from this constant, I have this m, which is the magnetic quantum number, which depends on the state of the system, and then Bz, which is the strength of the applied external magnetic field. So, the now what have I got from this exercise is that I have got an expression for the energy levels of hydrogen atom when I subject this hydrogen atom to an external magnetic field. Let us write down this new energy E prime, which is the old energy, the energy of hydrogen atom in the absence of magnetic field, plus beta m Bz, where beta is my Bohr Magneton, Bz is the external field that I am applying, m is the quantum number. Now, you look at here n, the energy level depended only on n quantum number, the principal quantum number. But when I apply magnetic field, in addition to this n dependence, I have also m dependence. But as you know, I cannot define my m without defining L, because m is defined only after I have defined my L value. So, therefore, in this case I give these indices to the energy levels as that E prime, the new energy level, that is the energy level of the hydrogen atom in the presence of external magnetic field, would have dependence on N, L and M all. Let us see, we know that in the absence of magnetic field, so we have this energy level corresponding to 1s orbital, then we have this energy level corresponding to 2s orbital and the energy levels corresponding to 2p orbital. So, this is 2s and 2p are degenerate only for hydrogen atom or any hydrogen like atom. This kind of degeneracy, that the energy levels are independent of orbital angular momentum L, is manifestation of the fact that we have only one electron which is going around the central potential. So, if I had more than one electron, this degeneracy, that is the degeneracy between 2s and 2p orbitals, will be lifted. But in any case, for hydrogen atom, this is the energy levels that I have. So, these three levels of 2p are different by their magnetic quantum number m. So, m is 0, m is plus 1, m is minus 1. All right. Now, in this case, so hydrogen atom in the absence of magnetic field, in this case when I record the emission spectra of it, I would actually see one emission line, and that emission line will happen at this energy difference, let us call this E. So, if I plot this energy the spectra corresponding to this emission, so I would get one line at the energy E, which will corresponding to the energy difference between these two levels. I of course know the energy level of the energy of this level, which is minus E0 divided by 4, which is n square, that is minus 3.4 electron volt, and this energy level is minus 13.6 electron volt for hydrogen atom. Now, I would get, in the absence of a magnetic field, I will get one line here in the emission spectra. What happens when I apply external magnetic field? When I apply external magnetic field, my energy levels become En, that means the original energy, plus some other term. Let us see how it changes. For example, when I look at the effect of 1s level, the 1s level will simply remain unchanged. Why? Because 1s level, 1s orbital has m quantum number as 0. So, En plus m is 0, 0 into this constant is 0. So, therefore, this energy level did not change 1s. What about the 2s level? In case of 2s level also, I would say since 2s level has m value 0, because L is 0 and therefore, m is 0. So, I get 2s level over here. What about 2p? So, I had these 3 2p lines, one corresponding to m is 0, plus 1, minus 1, these 3 levels. So, I have 3 levels. Let us consider first the energy of that level where m value is 0, when for 2p level. So, when m value is 0, so this term is 0. So, therefore, this remained unchanged. When m is plus 1, so I have the energy En, which is starting from this energy plus a factor. So, this corresponds to m equals plus 1, this corresponds to m equals 0, and when m is minus 1, you would see the new energy is the energy of the level in the absence of magnetic field, which was this, and then the term that I have here. What is the energy of this? So, this is still E2, because this is E2 minus beta Bz, and this is E2 plus beta Bz, where beta is the Bohr Magneton, which is a constant, and Bz is the external field. So, the energy levels are splitting by beta Bz, the magnetic levels. Now, when I record the emission spectra in this case, I now have a different situation. Here what did I have? What I had 1s level and 4 levels in this case, and I see a 1 line. But here in this case what I see is that I would get of course, I would get one line that is coming from here to 1s level, another emission from here, and the third emission. So far we are discussing only from the 2p level, because there exists some selection rules that will come to when we are discussing in more detail about spectroscopy. So, here what we would get is that we are getting 3 different emission lines. If I plot them, if you notice, this energy line will appear at the same value of E that it appeared in the absence of external magnetic field. Why? Because this energy level corresponds to m equals 0 of 2p level, and when m equals 0, the energy did not change. So, whatever the energy was here, that energy would still remain here in the presence of magnetic field. Now, when I look at m equals minus 1 emission from m equals minus 1, I see that I will get another line, whereas E minus beta Bz, and then from m equals plus level I will get another line at E plus beta Bz. So, what I see is that instead of observing one emission line in the absence of magnetic field, I am observing 3 emission lines in the presence of magnetic field. So, this is in the presence of magnetic field, and this is in the absence of magnetic field. Now, the difference is that when I apply magnetic field, my energy level starts splitting, and another important point is that I can control now the splitting between these lines. How can I do that? Because I see where while beta is a constant that I do not have any control over, but what I have a good control over is the value of the external magnetic field. So, if I wish to have this energy separation by some value, I can always calculate this beta Bz value or the value of the magnitude of the external magnetic field that I would apply to this system, so that I can obtain the desired splitting. So, for example, if I wish to get 1 centimeter inverse splitting, I want this one the splitting between the two lines as 1 centimeter inverse. So, this in this case it is simply beta into Bz, and the value of Bz is 1 centimeter inverse divided by the value of beta. So, I have to convert, since I know beta value in Joule per Tesla, I must convert this 1 centimeter inverse to the Joule unit, and when I do that you would find actually the value of the magnetic field which would come around about 2 Tesla of magnetic field. So, depending if I increase the magnetic field, the spacing between these two lines would increase. If I decrease the magnetic field, it would decrease. So, what we learned in today's class is that if we had correct formulation of the hydrogen atom, which is given by the quantum mechanical formulation that we carried out in last few classes, we are able to explain the splitting of emission line in the presence of magnetic field, or known as Zeeman effect. To remind you that this Zeeman effect could not be explained by Bohr's atomic model because of some of the flaws that we had discussed in Bohr's atomic model in our earlier class. We will continue our discussion in the next class to see what more effects we still have in this hydrogen atom problem. They will be the topics of our discussion in our next classes. Thank you for your attention.